So what are we going to talk about today? We are going to talk about mathematical induction. We'll basically see what this induction is about. So let's motivate with an example. All right. So here we go. So question is, what is the sum of first and odd? All right. So let's work on that. So let's look at this. So let's try to get a conjecture going. What should it be? So when n is so when first you look at the first integer, it is going to be 1, right? If you look at second, then it's going to be 1 plus 3, which is what? 4, right? We are adding odd integers. So sum of first two odd integers, right? Now sum of first three odd integers is going to be 1 plus 3 plus 5, which is going to be what? 9. Sum of first four odd integers, we have 1 plus 3 plus 5 plus 7, which is 16. Yeah, you can already observe a pattern. If not, let's go for another one. 5, 1 plus 3 plus 5 plus 7 plus 9. So it is 16 plus 9, which is going to be 25. So it seems that this is basically, seems like the first, this is n1 square, right? Yeah, this is 2 square. This is 3 square. This is 4 square. Yeah. So seems like the sum of first n odd integers is basically what? N square. Yeah. So let's try to, so we see this formula, or if I want to write it in terms of, so odd integers are written by 2n, so 2i minus 1, right? Yeah, and I can go from 1 to n. So this is sum of first n odd integers, and we have figured out the formula is what? Yeah. So for all n in, of course, we are interested in z plus, right? Because we are talking about adding positive integers. Okay. So this is, again, we haven't proven this. Do you see that? This is not a proof. Yeah. We see some pattern. We are seeing a pattern. We are observing a pattern. And based on that, we are making a conjecture, right? So now, so this guess has to be basically what? Proven, right? So how do we prove this, such a thing? All right. So in mathematics, there are two ways of proving things. Particularly mathematical induction comes handy when you have already a conjecture and you just want to prove it. Yeah. Sometimes what happens, so there are two ways to solve problems, right? So sometimes you may have a summation formula, you will work out everything and the answer turns out to be n squared. Second way of proving things, not all the time, but in the context we are working on, is we have some conjecture and we want to prove it for all n. Yeah, that's where you will see that mathematical induction comes into the picture. Okay, mathematical induction is like you're given a formula and you're proving it. How did the formula come about? Sometimes it is possible to know, sometimes it's not possible to know, or sometimes it's possible to know, but it's difficult to get to it. So mathematical induction is actually that tool. It helps you to basically what? Once you have a conjecture, it lets you prove things. All right. But of course, you're proving only for a subset of integers. And usually subset of positive integers. Yeah. Does that make sense? Yeah. So that is the gist of mathematical induction. Yeah. So let's try to look at it. So we need to prove our guess in general case, right? And notice that the problem of this type mathematical structure, which relies on the previous structure. What do you mean by that? You see, you have 2 square, and then you add, and you're getting what? You're getting to 3 square. And you can see that you're looking at the previous one, and then making a guess for the next one, and so on and so forth. Okay. So somehow using the previous structure to get to the next one. Okay. So this basically leads to the concept of, you'll see what mathematical induction is. I haven't said anything yet, but this is the underlying motivation for mathematical induction. So let's see what it is. So before we look at mathematical induction, we want to talk about something which is called well ordering principle. So what is the idea behind the well ordering principle? The well ordering principle says the following. It says every non-empty subset of non-negative integer has at least a least element. That means what? Take any subset. Okay, let's take any subset of non-negative integers. Okay, say 1, 3, 5, 9, 1, 22, 3, 1000. Yeah, it is, this set is finite, so of course it has a least element. You can find that out. Even if it is an infinite set, you can find the least element. Okay, and this is a property of only what? Non-empty subset of what? Of non, sorry, it's a property of a non-empty subset of positive integers. Yeah, non-negative integers are positive integers. Yeah, you can include zero, you can throw in zero if you want to, right? Not a big difference. So this is the idea behind the well ordering principle. Note that this property is not this property is not true for every set. For example, if you take set of rational numbers, yeah, and I can give you a set 1 by n where n belongs to. So this is a subset. Well, look at this subset, right? Yeah, this is a subset of rational number. Do you agree? Yeah, let's just see what it looks like. It looks like 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, so on and so forth, right? You can't tell me what is the least element here. Why? You say one may be tempted to say, oh, 0, but 0 is not here. 0 can never be written as 1 by something integer, right? And moment you take anything positive, you can't. I can always find a number which is, I can always find 1 by n which is smaller than that. So again, this property is very special. This property of what? The property that every non-empty subset of non-negative integer has a least element. Okay, this is called well ordering principle. Okay, so this is the idea behind the well ordering principle. All right, that again, I'm repeating the same thing. If you take a non-empty subset of non-negative integers, then it will always have a least element. Okay. Now, why are we asking about that here, right? Why are we discussing that? Because that's what the nature of mathematical induction is. So what is a mathematical induction? So it is a technique to prove basically a statement for all x where x is coming from either the set of positive integers or set of non-negative integers, right? Or yeah, so it's a statement you want to prove for all non-negative integers, let's say. Okay, so for example, if I go back to our previous problem, we are trying to say for what? For all x or for all n, we are trying to prove a statement. What is the statement? That summation and I going from 1 to n of 2i minus 1 is n square. This is our statement Pn, right? Or you can say x, you can replace that n by x, right? So this is a statement for all n where? For all n in your universe is basically z plus. Yeah, or in particular here, you're starting with 1, so you are basically going from 1 to onwards. So this is a statement, all right? All right. So now how do we prove this statement? So the way to prove this statement is the following. You prove this statement. So this is what the mathematical induction is. Yeah, you want to prove a statement for all n. Yeah, where your universe is either the set of integers, positive integers, my bad, or it's some big chunk of positive integers. So here we go. How do we prove it? So there are steps to it. One step is a base case. So base case is you prove for the smallest element in your universe. Yeah, generally, most of our problems, it will be 1. Yeah, but as I said earlier, you could be starting from 3, 4, 5. Yeah, and the smallest element is guaranteed because of what now? Because of well ordering principle. That is where the well ordering principle comes into the picture. Does that make sense? Yeah. You want to see, the idea is that the mathematical induction goes like this. You want to prove it for the base case. That means you want to prove it for the smallest element in the set. Okay, that is what. So you prove for the base case. So let's try to see this, work it out together at the same time and see what happens. Okay. So base case is what? So in this case, we will prove what? P1, right? Let's check. Is P1 true? So LHS for P1 is what? Summation I going from 1 to 1 of 2I minus 1. That is simply what? You're just putting 1, right? So you get what? 1 on this side. And RHS is what? RHS is going to be 1 squared. Yeah. So we get P1 is true. Yeah. I mean, why? Because LHS is RHS. Not necessarily. I mean, but it's a good idea to show that. Yeah. I mean, it's not really convention, but it's a good idea to show that this is equal to this. Yeah. I mean, you are making a statement. Sometimes it's a good idea to do that way. Sometimes you'll see that you don't need to really do LHS, RHS. You can do it in other ways as well. Okay. Now the base case is true. Now notice the second step is induction hypothesis. So in induction hypothesis, what you do is you assume it true for K. So assume it to be true for n, or let's say for n equals to K. This is assumption. There's no proof required, okay, for this part. That is what? That is, you're saying P K is true. Yeah. Then the third step is prove. So you're basically prove for n equals to K plus. Okay. So yeah. So now we are trying to, so from induction hypothesis, we are trying to prove that it's true for n equals to K plus 1. Okay. So let's prove now. So what do we have? Since Pn is true, Pk is true. Let's see, what does it mean by Pk is true? That is, we are assuming this, right? That means summation I going from 1 to K, 2I minus 1 is K squared. Yeah, this is our assumption. Yeah, assumption means you don't need to prove it. Now we need to prove for what? K plus 1. So let's see, how will you prove for K plus 1? So we have summation I going from 1 to K of 2I minus 1 equals to K squared. Yeah. Now, what is the next term here? So, no, next term will be, how will the K, so if I write K plus 1, how will that look like? So that's going to be summation I going from 1 to K, 2I minus 1. And I want to add K plus 1 term, right? So how will K plus 1 term look like? 2 times K plus 1 minus 1. This is a K plus 1 term, right? If you don't like this, you can see the following. Let's look at the summation I going from 1 to K of K plus 1 of 2I minus 1. Yeah, is that okay? In that case, we'll start with LHS and go to RHS. Yeah, let's start with this. LHS goes to this. Now, what we'll do is we will try to recycle what we have gotten earlier. So I will go to K. And then what is the K plus 1 term? When I put K plus 1, what will I get? I get 2 times K plus 1 minus 1. Yeah. Do you agree? Why am I breaking it like this? Because I want to use this part here, right? I want to be able to use this induction part, right? Assumption part. So now what is this going to be? Right? So let's see, what do we really want to prove? We want to prove that if we go from I going from 1 to K plus 1 to I minus 1, that's going to be K plus 1 the whole square. This is what it means by pk plus 1 is true. So what we'll do is we will try to take this here and then show that it is equal to what? K plus 1 square. Does it make sense? And how are we going to do that? Yeah. The way we are going to do that is we are going to use this part here, right? How are we going to do that part? We will basically break it from I going to k plus 1. So we'll take a pause at k, for which we have a substitution, and then check out that becomes what? K plus 1 whole square. That's what we want to do. Okay. So let's go about it and see if it works. So this part becomes what? K square plus 2 times k plus 1 minus 1. That's going to be k square plus 2k plus 2 minus 1. That's going to be k squared plus 2k plus 1, and which is your k plus 1 the whole square. Yeah, and that is your RHS, right? Therefore, what? Therefore, p k plus 1 is true. Therefore, by mathematical induction, p n is true for all n. Well, in our case, what is our space? Our space is Z. So these are the steps of mathematical induction. Does it make sense? Yeah. So the steps are, again, let's go through it. You prove for the base case. You assume it true for k, assume, and then using that, you prove for, assuming true for k, you want to prove for k plus 1. Okay. So this is the principle of mathematical induction. Okay. Now, if I want to write it in the logical sense, in the sense of logical inference, what are we having here? Let me write down. So P of n naught right? And then we have what? Pn implies P of n plus 1. This means what? Pn is true for all n. Yeah, is that okay? So that is what is happening here. Yeah, this is the idea behind mathematical induction. Let's try to write a proof for this statement. That summation I going from 1 to n of I is n into n plus 1 divided by 2 for all n belonging to Z. Okay, and there's an emphasis on how to write this statement as well. So let's see. So what is our statement we want to prove? To prove that our Pn is, what is our statement? So our Pn is, so Pn is the following. So Pn is that summation I going from 1 to n of I is n into n plus 1 divided by 2. Yeah, where n actually belongs to what? N belongs to Z plus. Okay. So again, here we start step 1. So it's a good idea to write step by step. So step 1, base case. Yeah, here you see the base case is already what? Base case, when you write it like this, the base case is 1. Yeah, makes sense? Now, base case. So let's see P of 1. P of 1. So again, I want to say P of 1 is true. That means I want to show that left-hand side is equal to right-hand side, right? Isn't it? That's why I use LHS and RHS. So let's see. LHS is going to be summation I going from 1 to 1, because n is 1, of I. And that's simply going to be what? Isn't it? You start your engine at 1. Then you go, okay, what is the next one? The next one is after 1, there is nothing else. So this will be only one summation. Does that make sense? Yeah. Yeah. Is the summation, are you comfortable with the way summation works? Anyone who's not comfortable? LHS is this. And what is my RHS? RHS is is basically 1 into 1 plus 1 divided by 2, which is going to be 2 divided by 2, 1, right? So we have, since LHS equals to RHS, that is left hand side is equal to right hand side, we say P1 is 2. Okay. Now, next step is step 2, is induction hypothesis. So the idea is, what we do here, we'll say basically assume PK is true. Okay. That means what? That means summation, that is summation I going from 1 to k of I is going to be k into k plus 1 divided by 2. Is that okay? So this is induction step. You don't need to prove anything here. Step 3 is proof for what? Proof for k plus 1. Yeah. So now how do we do this? Well, you can either go from LHS to RHS, or you can take the previous one and add k plus 1 on both sides. How do you want to do it? That's totally your choice. Okay. But first, I think it's a good idea to see what do you really want to prove. Okay. What do you mean by proving for pk plus 1? So that means what? So we want to prove that p of k plus 1 is true. So we should figure out what do we really want to prove. We want to prove, I'm going to write it on the side, summation I going from 1 to k plus 1 of I is going to be what? Wherever there's k, there will be what? K plus 1. So k plus 1 times k plus 1 plus 1 divided by 2. This is what I need to prove, right? Yeah, because this is my k, new k. Does that make sense? Yeah. So now let's try to see how will we prove it. You can start whatever. I mean, you can either take LHS and show that it's equal to RHS. So we have, let's start with that. LHS is summation I going from 1 to k plus 1 of I. And now I'm going to break it as I going from 1 to k of I plus, what is the next term? It's k plus 1. Right? You all agree with that? I mean, the reason why I'm stopping at k, because I'm going to use this, I'm going to leverage this formula, which is basically given to me as a part of induction hypothesis. Does that make sense? Yeah. Without using pk, I'm not be able to, in most of the cases, I'll not be able to prove for pk plus 1. Yeah. So we need to use something from there, right? So this is what is coming here. Now, this part will be now replaced. This part is going to be replaced now, right? This is going to be summation I going from 1. So now that's going to be replaced by what? K into k plus 1 divided by 2 plus k plus 1. Yeah. This is because of what? This is because of induction hypothesis. This is because of step 2, right? Yeah. That it turns, you come from 1 to k, it becomes k into k plus 1 divided by 2. All right. Now we need to simplify this to make it look like the RHS. So how do we do that? We have k plus 1, take k plus 1 common. What is left in the bracket? K by 2 plus 1. Do you agree? Yeah, pull out k plus 1 common. Now let's organize this. So it's going to be k plus 1 times k plus 2 divided by 2. Yeah, isn't it? I'm going to cross multiply this and then make it k plus 2 divided by 2. It's dividing this part, that means dividing the whole thing. And then I can write it to make it look like what? K plus 1 plus 1 divided by 2, which is my RHS. Right? You agree? So therefore, what? Pk plus 1 is true for all n. pk plus 1 is true, I mean, therefore by induction hypothesis, Pn is true for all n in So the point is the following: why the base case is important. So proving for base case is important. Let's see. Suppose I do not prove for base case. Suppose my Pn is a statement that n equals to n plus 1. Okay. Yeah. So I assume that pk is true. I mean, of course, we know that's absurd, right? N is not same as n plus 1, right? 2 is not same as 3, 3 is not same as 4, right? But say, suppose pk is true, then we can easily prove that pk plus 1 is also true. Why? Add 1 on both sides. We get what? N plus 1. pk, suppose, assume pk is true. Then pk plus 1, we add 1 on both sides. We get what? So pk is true. That is, it means that k equals to k plus 1. Yeah. Then we get what? Add 1 on both sides. We get n k plus 1 plus 1. Yeah. So I'm taking the previous equation and adding 1 on both sides. So what have I proved? I have proved that k plus 1 equals to. That means what? I have proven Pn. So I have proved that pk plus 1 is true. But this statement is clearly false. You see? So you have to prove for the base case, because without which this statement won't make sense. You can prove all kind of absurd things if you do not assume the base case. All right? Yeah. So sorry, if you do not, my bad. If you do not prove the base case, you have to prove the base case. Yeah. You can think about this as basically bunch of dominoes lined up. Yeah. So the idea is that if the second domino falls, then the third domino falls is guaranteed. The third domino falls, then the fourth domino falls is guaranteed. Right? So if nth domino falls, then n plus 1 domino is going to fall. That is guaranteed. But the first domino should be pushed down. Otherwise, none of them are falling, really. So that is an vague analogy of mathematical induction. It must be proof for the base case. Yeah. And then if pk implies true for pk plus 1, then by mathematical induction, it's true for all n. Okay. Is that making sense? Yeah. So any questions here? It's a slightly interesting concept. I'm going to prove something, this problem without induction as well, that summation of I going from 1 to n of I is n into n plus 1 divided by 2. Okay. So this is proof is going to be without induction, but again, I mean, like, but I just want to indicate that some of them you can do without induction, but for most of them, it makes sense to do by induction because it's simplest if you can have a proper conjecture. Let's say, for example, let's say I want to add this, huh? I'm going to add one summation I going from 1 to n of I. So let's write this. So 1 plus 2 plus 3 plus 4 all the way till n, right? This is a sum you're looking for, isn't it? Then let's write this sum in the other order. N into n plus n minus 1, n minus 2, all the way till 1. So I've written the same sum, but in the decreasing order now. Do you agree? Add now. So let's see. So addition of these two is going to be n plus 1. Addition of these two is going to be also n plus 1. Addition of this also will be what? N plus 1. All the way. Last one also will be n plus 1. How many of these terms are there? N of these guys. So 2s is n plus 1, n plus 1, n plus 1, n times. So it's n times n plus 1 is 2s. So therefore, s is n into n plus 1 divided by 2. That's one way of looking at it. Yeah. But again, as I said, I mean, like there are some problems for which we can't prove it. Well, I mean, we can prove, but it's easy to prove with the induction. Yeah. And some of them are like, okay. I mean, we could do it another way as well, just for the fun sake. Suppose I want to add 1 to what? 1 to n. So I have 1, 2, 3, 4. So I'm adding the number of dots, suppose, okay? So I'm going to basically make a perfect matrix out of it. I'm going to write 1, 2, 3. Four, right? So I'm adding 1 plus 2 plus 3 plus 4. And I'm also, again, crosses are also 1 plus 2 plus 3 plus 4, right? So in some sense, I'm basically doing what? I'm doing 1 plus 2 plus 3 plus 4, right? Isn't it? And now this is basically what? This is double of that number, right? So this is going to be what? So 1 plus 2 plus 3 plus 4 is actually, so double of this sum is equal to what? How many rows? 4 rows. Match with 4. How many columns? 1 extra column, which is what? 4 plus 2. Right? So you get what? 1 plus 2 plus 3 plus 4 equals to 4 into 4 plus 1 divided by 2. Right? I mean, like, of course, you can make this argument for any n if you draw it properly and argue. There's a little bit more argument required, but you can prove that as well. But again, the point I want to make is that for mathematical induction, the beauty lies sometimes that you don't even have to do all this hard work of finding the pattern. Do already summation I square or I cube. You'll see that there is slightly more refined argument required to prove those. Okay. Anyway, come back to, let's try to do some more problems now. Okay, so here we are. So prove that n is less than 2n for all positive integer n. Okay. So how do we do this? So same, we need to set up this as a mathematical induction. So let's try to set this up. So let Pn be the statement. Let me just do this one. So 7.5, so we're doing size 7.5. So let's set the statement. So we are having Pn is a statement that n is less than 2n. Okay. And what is my universe? We can say for all n belonging to z plus. This is what we want to prove. Okay. All right. So again, the same ideas will follow. Base case. N equals to 1. Let's try to prove it for base case. So we have what? P1 is what? LHS we get to be 1. And RHS is what? 2 to the power 1, which is 2. Yeah. So since 1 is less than 2, P1 is what? 1 is 2. Yeah. You agree with that? Now let's assume, let's try to, so next step is induction hypothesis. Where you're assuming, assume what P of K is true. Yeah, that means what are we assuming? That means we are assuming that K is less than 2 to the power K. Yeah, this is step 2. If you want to call this step 1, step 2. Let's try to look at step 3 now. Now we want to prove for what? And for K plus 1. Yeah. So now let's look at P of K plus. So now how do we prove it? Let's see. So again, let's talk about LHS. LHS is what? K plus 1. Yeah. Now we already know that K is less than, so this is going to be 2 to the power K plus 1. Do you agree? Yeah. Now here is a very interesting trick. Do you agree that this is less than 2 to the power K plus 2 to the power K? Because 1 is less than 2 to the power K, no matter what. Yeah. And then what do you get? What is 2 to the power K plus 2 to the power K? Is 2 times 2 to the power K, which is what? 2 to the power K plus. Yeah. This is a, you may think, oh, this is a wild approximation. Yeah, it's true. Yeah. Isn't it? So this is one way of basically. So P, so therefore what? Which is PK. So LHS. So therefore what? Therefore what? So we can say that therefore PK plus 1 is true. And therefore by principle of mathematical induction, that's what it's called, principle of mathematical induction. Pn is true for all n in